Hello. In this video I want to talk about the concept of a complex number. So where does this come from? Well, in the simplest terms, if we look at an equation like this one, x squared plus x plus 1 is 0. Right? It has no real solution. So in other words, there's no real number x that satisfies this equation. And we can see that simply by noting that the discriminant is less than 0. Right? So that means that if we were to apply the quadratic formula for the solutions of quadratic equations, we'll end up with an expression containing the square root of a negative number. And the real numbers do not contain square roots of negative numbers. So square root minus 3 does not exist as a real number. So in the very simplest terms, complex numbers is a way to handle this kind of expression. Now, what is a complex number? Well, a complex number is an ordered pair of real numbers. So we have two real numbers a, b. We write a first and then b, and that ordered pair gives us a complex number, or that is what we call a complex number. Right, so the first real number a, we call the real part of z, and write it rez. And the second complex number b, we call the imaginary part of z. So in other words, write that imz. And the set of all complex numbers is denoted by blackboard bold C. Right. So for instance, here we have two complex numbers, z and w. Right. So the real part of z is 2, and its imaginary part is 3. On the other hand, the real part of w is 3, and its imaginary part is 2. So you should note that these two are different complex numbers, right? Z's real part is 2 and w's imaginary part is 2. That doesn't mean that they're the same, right? In particular, we define equality of complex numbers as follows. Two complex numbers z and w are equal if when z is ab and w is cd. They're equal if a is equal to c and b is equal to d. So another way of saying this is to say that z and w are equal if and only if the real part of z equals the real part of w and the imaginary part of z equals the imaginary part of w. Right. So one should note that with this definition, when we say z is not w, what we mean is either the real part of z is not equal to the real part of w, or the imaginary part of z is not equal to the imaginary part of w. Okay. So now we're going to define some structure on the set of complex numbers. So we start off by defining how we're going to add these numbers. So the definition is very simple. If we have two complex numbers, z is ab and w is cd, then we add them simply by adding the real and imaginary parts, respectively. So z plus w is the complex number we get by adding the real parts of z and w. That gives us the real part of z plus w. Then we add the imaginary parts of z and w. That gives us the imaginary part of z plus w. Right. Fairly simple. So for instance, if z is 3, 4 and w is 8, 6, then z plus w is 3 plus 8 for the real part, and 4 plus minus 6 for the imaginary part. So that gives us 11 minus 2. Okay. Now, you may have noticed that this is all very familiar, right? So what is the difference between the complex number, which is the ordered pair z is ab, and the vector z bar, which is the ordered pair A, B, and R2. Well, superficially, you know, for the complex number, we don't put a bar on top, while for the vector we do. For the complex number, we have round brackets, and for the vector, we have triangular brackets. But these are superficial differences. Right? At heart, up to now, there's no real difference. Right? But what we're going to do next is introduce more structure on the set of complex numbers, right? And that is where the difference comes in. Up to now, you can view this ordered pair A, B either as a complex number or as a vector, right? But now we're going to do something new, something we haven't done for vectors. We're going to define multiplication for complex numbers. And how do we do that? Well, it's slightly more strange than addition. Well, we have our two complex numbers, Z is AB and W is CD. Now, how do we multiply them? Well, for the real part of ZW, we take real part Z, real part C. We multiply them. Now we take imaginary part Z and imaginary part W, we multiply them and subtract. Right. And that gives us the real part of Z times W. So it's real times real minus imaginary times imaginary. Right. Now for the imaginary part of Z times W, right, now we take real part Z and imaginary part W, and we multiply them. And now we take imaginary part Z and real part W, we multiply them and add it to our previous answer. Right? And that's the complex number that we call Z times W. Right? It looks strange, but as we'll see, it turns out to be exactly what we need. Okay, so let's do a short example. We've got Z is 3 minus 2, W is 4, 1. Let's calculate ZW. Right, so it's 3 minus 2 times 4, 1. Right, so it's real by real. So 3 times 4 plus imaginary, not plus, minus imaginary times imaginary. That gives us the real part of Z times W. And now for the imaginary part, we take real Z, imaginary W, plus imaginary Z, real W. Right? So this is going to give us what? 12 plus 2, so 14. And this is going to give us 3 minus 8, so minus 5. Right. There we go. Now, we call these ordered pairs with addition and multiplication, as we've defined it, complex numbers. Right? So we can sort of justify that name by noting that if we look at the properties of addition and multiplication of real numbers, then complex numbers also have all of those properties. Right? And you can refer to Theorem 611 on page 232 of the notes. Right? So an example of this is what we call the distributive law. And what does this say? Right? Basically, it says we can multiply into brackets. So if we have three complex numbers, Z is AB, W is CD, and Y is EF, then Z times W plus Y equals ZW plus ZY. Right? So note here that we first do the addition and then we do the multiplication. Whereas here we do multiplication, multiplication, and then addition. Right? So we're basically multiplying into the bracket. Right. Now, to see that this is so, we just apply the definitions of addition and multiplication for complex numbers. Right. So we start with the left-hand side. Right. So if we add W and Y, what do we get? Well, W is CD, Y is EF. So by definition, their sum is C plus E, D plus F. Right. And now we just say, okay, well, now we're interested in Z times this complex number W plus Y. Now what does that look like? Well, we just take the definition again. Right? Z times W plus Y. So Z is AB. W plus Y, we've just shown, is C plus E, D plus F. Right, and now we apply the definition. So it's real minus imaginary, and then it is real imaginary plus imaginary real. Okay, and now we can just use the arithmetic rules for real numbers to simplify this a little. So that's AC plus AE minus BD minus BF, and this is AD plus AF plus BC plus BE. Okay, and let's call this expression 1, so we can refer back to it later. And so this is just about as far as we can go with the left-hand side. Now let's look at the right-hand side. Right, so the right-hand side contains ZW and ZY. Right, so ZW, so that's AB times, and W is CD. So we apply the definition of multiplication, gives us AC minus BD, and AD plus BC. And likewise for ZY, it's AB and EF. We apply the definition of multiplication, gives us AE minus BF and AF plus BE. And now we just apply the definition of addition, right, to these two expressions. So now we say, well, what is ZW plus ZY? Well, we just add. So we've got ZW is AC minus BD, AD plus BC, plus ZY, which is AE minus BF, AF plus BE. We apply the definition of addition. That gives us AC minus BD plus AE minus BF, and the imaginary part is AD plus BC plus AF plus BE. So now let's see. If we go back and we look at what we have here for Z times W plus Y, right, we've got AC, AC, AE, AE, minus BD, minus BD, minus BF, minus BF. So the real parts are equal. And we've got in the imaginary part an AD and an AD. We've got a BC and a BC. We've got an AF and an AF, and a BE and a BE. Right. So this is going to be equal to Z times W plus Y by 1, and we're done. Okay. Now the other properties of addition and multiplication of complex numbers follows essentially the same argument, or the same type of argument. And you may note that if you go back to the proofs for the properties of vector addition and scalar multiplication, then it's also based essentially on this kind of argument. So there's basically nothing new except we have a funny definition of multiplication. And we'll talk about this funny definition of multiplication in a subsequent video.